Good morning. Today I am going for presenting on theory and interpretation of nuclear magnetic resonance spectroscopy. I, Dr. T.Y. Pasha, Professor and HOD in the Department of Pharmaceutical Chemistry, Sri Adi Chunchanagiri College of Pharmacy. As a part of an introduction, a nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize organic molecules by identifying the carbon hydrogen frameworks within the molecule. Two common types of nuclear magnetic resonance spectroscopies are used to characterize organic structures. One among them is proton NMR. The second one is the carbon 13 NMR. Proton NMR is used to determine the type and the number of the protons in a molecule, whereas C13 NMR is used to determine the type of carbon atoms present in the molecule. The source of energy in the NMR is radio waves, hence which have a long wavelength and thereby they have got low energy and low frequency. When a charged particle such as a proton spins on its axis, it creates a magnetic field. Thus, the nucleus can be considered to be a tiny bar magnet. Keeping this and taking the advantage of this bar magnetic nature of a nucleus, we go for exploiting the nucleus by application of the external magnetic field. Normally, these tiny bar magnets are randomly oriented in space. However, in the presence of a magnetic field, that is B0, we represent by B0, they are oriented with or against the applied magnetic field. More such nuclei are oriented with the applied field because this arrangement is lower in energy. If you look at here, that the rotation of a nuclei with respect to that of the bar magnet, and the nucleus before application of the external magnetic field, the nucleus are in random motion. On application of an external magnetic field, the nucleus are arranged or oriented with the direction of an applied magnetic field. In a magnetic field, there are now two energy states for a proton. A low energy states with the nucleus aligned in the same direction as B0, and high energy states in which the nucleus aligned against the B0. When an external energy source that we represented as HV that matches the energy difference between these two states is applied, energy is absorbed and causing the nucleus to spin flip from the one orientation to the another orientation. The energy difference between these two nucleus will be correspondent to the low frequency radio waves, and hence we get the electromagnetic spectrum. Whereas in connected to the in the continuation of the introduction of NMR spectroscopy, the two variables characterize the NMR, that is an applied magnetic field B0, the strength of which is measured in Tesla, and the frequency we represented of a radiation used to resonance, they measured in hertz or in megahertz also. Radio frequency waves ranges from kilohertz to the megahertz and also in the microwaves. The frequency of the light needed for a resonance and the applied magnetic field strength are proportionally related, like as it's symbolically represented with the formula that the frequency of the light is directly proportional to the applied magnetic field. The stronger the magnetic field, the larger the energy difference between the two nuclear spin states, and the higher the frequency needed for the resonance. NMR spectrometers are referred to as 300 megahertz instruments, 500 megahertz instruments, and so forth, depending on the frequency of the radio frequency radiations used for the resonance. Just I am putting here and representing and projecting you the picture of an NMR spectrometer, which is commonly used for recording the proton types of the proton present in the molecule, as well proton and as well as the carbon atoms present in the molecule. That an NMR spectrometer in which a sample is dissolved in a solvent. Usually we use CDCl3, that is the deuterated chloroform, and we will be applying the radio frequency generator, then irradiates the sample with the short pulse of radiation, causing the resonance. And hence, once the radiations are applied, there will be a alignment of the nucleus with respect to that of the applied magnetic field. And by looking into the difference of absorption energy from the lower state to the higher energy, and the released energy will be recorded in the detector and measures the energy released, and the spectrum is recorded. Protons in the different environments absorb at slightly different frequencies, so they are distinguishable by NMR. This is the most interesting point to be considered with reference to the measurement of, or the identifying the type of the protons and the number of the protons present in the molecule. What I mean to say is that if you look at if you consider a simple molecule, like it may be in a methanol to ethanol, ethanol, or any kind of a molecule, if you consider it, no doubt there will be protons are present, but the environment of the proton differs from one to another. We'll look into the one example and we'll come to know that the equivalent protons and the non-equivalent protons present in the molecule. The frequency at which the particular proton absorbs is determined by its electronic environment. Yes, indeed, it is very much important point to be considered in connected to the appearance of a signal in the NMR spectrum is depending upon the type of the proton, and type of the proton means that the electronic environment of that particular proton present in the molecule. Further, the modern NMR spectrophotometer uses a constant magnetic field strength, constant magnetic field strength, and then the narrow range of frequencies applied to achieve the resonance of all protons. Look at here, the simple NMR spectrum is designated and projecting over here. An NMR spectrum is a plot of the intensity of the peak against its chemical shift, measured in parts per million, and usually we represent that as a ppm. This simple NMR spectrum has got the two parts, like we designated here as an upfield direction and the low downfield direction, and the lower scale, the x-axis, is also represented here. The ppm's values, it starts from 1 to 10, and this is called it as a delta scale, and usually we represent as a in the form of a chemical shift. Now, with reference to the spectrum which I projected, I wanted to say that the NMR absorptions generally appear as a sharp peaks, okay, and increasing chemical shift is plotted from right to left. What does it mean? Increasing chemical shift is plotted from right to left, but that is the values, the ppm values is starts from 1 to 10, that is from right to left, and the most protons absorbs between the 0 to 10 ppm. This is with reference to the proton NMR. Okay, most of the signals, we, instead of saying as in peaks, we can say as in signals. The signals for a particular proton appears maximum in between 0 to 10. In the rare cases, it goes beyond 10 up to 11 to 12, not more than that. Whereas the carbon NMR scale is entirely different, comparing that of the proton NMR scale. That we shall see it when we go for discussing this particular part. And in the NMR spectrum, as I have mentioned, the two things, that is upfield and the downfield. That is, the terms upfield and downfield describes the relative location of the peaks. Hope you are getting this point. Okay, the terms upfield and downfield describes the relative location of the peaks. Upfield means to the it represents to the right. Downfield means it represents to the left. NMR absorptions are measured relative to the position of a reference peaks at 0 ppm on the delta scale due to the tetramethylsilane. Tetramethylsilane is always used as a standard. The reason behind is that it is a volatile inert compound that gives a single peak at the upfield direction from the typical NMR absorption spectrum. It has been taken as a 0. Okay, and as this tetramethylsilane has got the 4 methyl groups with the silicon SA group in the center, and known to be in a most inert solvent with respect to the organic compounds which we take it, which we dissolve it in a particular solvent. Then the chemical shift of the x-axis gives the position of an NMR signal measured in ppm according to the following equation, that the chemical shift can be measured by following with a simple formula, that observed chemical shift in hertz divided by frequency of the NMR spectrometer. 4 different measures of the proton NMR spectrums are provided information about the compounds, that is that number of the signals. I repeat, 4 different features of a proton NMR spectrum provides the information about the compound, that is compound structures, that is about the number of signals, position of the signals, intensity of the signals, and the spin splitting of the signals. It means that the number of the signals are usually directly proportional to the type of the number of the protons present in that. The position of the signals indicates the electronic environment of the proton present in the molecule. Similarly, the intensity of the signal is also related to the electronic environment of the environment of the particular proton present in the molecule. Now, keeping that point in view, just let us have an introductory part of this in connected to the signals, that the number of NMR signals equals the number of different types of the protons in a compound. Very interesting and point to be considered over here, that the number of, I repeat, the number of NMR signals equals to the number of different types of protons in a compound. And then the protons in different environments give the different NMR signals. Unless we don't see the NMR spectrum, it is difficult to sense this, but still the concept is very much clear, that the number of the signals present in the particular NMR spectrum is depends upon the type of the proton and its environment. Okay, then the equivalent protons gives the same number of signals. Now look at here the word like equivalent. When we are introducing the term like equivalent protons, there should be also a non-equivalent protons in the molecule. Okay, keeping that point in view, in order to justify that, here I have put here the one example, like ether molecule is taken over CH3O CH3, right? This, in this case, the proton environment are equal, thereby the all equivalent protons, since all the protons, though there are 6 protons but the environment is same, thereby if you subject this ether molecule to the NMR spectrometer, we get only one signal. Because of similar protons. Now let us go for the another molecule like chloroethane. Okay, in this chloroethane, what I have represented here, that the HA and HB. HA and HB means that the type of the protons, are they similar or different? If you look at the structural formula CH3CH2Cl, that is chloroethane, the proton of HB is different from that of the proton of HA. Thereby, when you subject this chloroethane to the NMR spectrometer, we get two signals. Similarly, the third example which is quoted over here, that is methyl ethyl ether. This is a methyl ethyl ether, and this methyl ethyl ether has got 3 types of protons, and those 3 types of protons are represented here as HA, HB, and HC. Why I am saying there are three types of the proton? Look at the proton environment of this proton to this proton and these two proton. Okay, this proton, particularly Hb proton, okay, though it is attached to the oxygen atom, electronegative element, and here this Ha proton is also attached to the oxygen element, but the Hb proton further it is associated with the Hc proton. Thereby, its environment is bit different because it is influenced by the Hc proton also. Thereby, the methyl ethyl ether has got three types of proton, and the same has been represented as Ha, Hb, Hc. And further, to determine the equivalent protons in a cycloalkanes and alkenes, one should always draw all bonds to the hydrogen. That is what if you just say as an orally cycloalkane, unless we do not draw the cyclic structure, it is difficult to know that whether the proton of the environment of the proton is similar or different. That's why it is mandatory to draw the structure of cycloalkanes or the cyclic structures, and thereby we can see that whether they are similar or different. Look at here, the like this is one example which I drawn over here is cyclopropane. Okay, cyclopropane. When you subject the cyclopropane, we get the two signals, and similarly if you look at this is a chloroethene molecule, and this chloroethene molecule has got three types of protons over here, and thereby we get the three signals. And in the continuation of this, let us look at here. In comparing to the two protons on a ring or a double bond, two protons are equivalent only if they are cis to the same group or trans to the same group. What is this cis and trans? As we are very much aware that the trans are the compounds where if the similar groups are in opposite direction, cis groups, compounds are those where the similar groups are present at the same part or in the same direction. Keeping that point in view, even the NMR also helps to determine the cis and trans isomeric form of the compound. That is, keeping with reference to that, here I have written, here I have represented some three examples. That is like one dichloroethylene. Okay, one dichloroethylene. The structure is also represented here, but though there are two protons are present here, but the environment of these two proton is similar. Why? Because this proton is also cis to the chlorine, and this proton is also cis to the chlorine. And whole, if you look at the structure and the environment of this proton is similar, thereby we get only the one NMR signal for this one dichloroethylene compound. Similarly, now if you go for this molecule, okay, the one bromo, one chloroethylene, one chloroethylene. No doubt, both are cis to the respect to halogens attached to the respect to carbon atom attached to the double bond, but the type of the halogen present over are different comparing with that of the first structure. Thereby, the environment of this proton, Ha proton, and environment of this Hb proton is different. Since they are both are different, we can consider that there are two types of protons present in this one bromo, one chloroethylene. Since two protons, we get the two NMR signals. And similarly, the third example, look at here, the most interesting, that it is saying that is the chloroethylene molecule. Chloroethylene molecule, that is this chloroethylene molecule has got the three protons, and the environment of the three protons is entirely different to one another. Thereby, I represented here as an Ha proton, Hb proton, and Hc proton. Why it is so? That why we get the three types of protons? Because this proton is cis to the chlorine, whereas this Hc proton is cis to the Ha proton. But this Ha proton environment is different. Thereby, though it is a cis type of a compound, but we get the three signals.